In section 3.9, we're going to look at how to approximate a function with the tangent line or with a linear function. So in this section, we're going to find and interpret the local linearization of a function at a point. So here's the main idea. We can approximate a function f of x at a x value x equals a with the tangent line of that function at x equals a. The reason why we may want to do this is because the function itself may be difficult to deal with, or more realistically, we may not know all the information about the function. We may not know exactly what function it is. But a line, the tangent line, is the easiest kind of function we can deal with, and we learned everything about lines in an Algebra 1 course. And they're very nice to deal with and very easy to find values for. So there's going to be a lot of kind of terms thrown around here, and there's lots of terms thrown around in different texts. This idea of linear approximation or tangent line approximation is the exact same idea as local linearization. And I want to take a second and talk about why these terms are used. Specifically, what does local linearization mean? So local means that we are near something. If you go to your local grocery store, you're going to the grocery store that is near you. So this is saying something near something is linear. Near a point, something is linear. And this is the idea that if we look at a function like x squared, that is not a linear function. But if we could zoom in on a piece of that function, we would see that this is starting to look maybe more linear. In fact, it's more like that there. And if we could zoom in even further, we would see that this function is starting to look more and more like a line. And we could do it maybe even once more. And at this point, there's really no difference between the function itself and a line. And the line that we have here is exactly the tangent line to the function at that point. So that's what that term means, but it really is the same idea that we're going to use a tangent line to approximate a function. And we can see that if we are really near a function or near a point, the tangent line and the function are almost the exact same thing. And the closer we get into it, they really become even more close. Far away from that point, it's not going to be the same thing, but near that special point where the tangent line hits the function, we have a good approximation. And we're going to use that tangent line to approximate the function value. So let's see how I could do that. Example 1, estimate the value of square root of 1.01 with a tangent line. And the idea here is that we don't know the value of square root of 1.01 without a calculator. It's not a nice kind of value to deal with. So we could use a tangent line to find a better approximation for that. So the function that we are talking about here is square root of x. And we are going to be using the tangent line of square root of x at a nice value. How about x equals 1? That's a nice value to deal with. We know what the square root of 1 is. So we're going to use that nice value and use the tangent line at that point. So if you draw a graph, in fact, if we go back to the previous page, we can look at that graph. Think about square root of x. Think about x equals 1. Think about x equals 1.01, which is going to be very close to it. We're going to try to estimate that point. That y value is what we're going to try to get. That's our answer. But we're going to use the tangent line at 1, which is going to give us another point to deal with. We're actually going to be finding that point is going to be our answer, the point that lies on the tangent line. All right, so this is our actual value. This is going to be our approximation. All right, so let's see how this is done. First, we need to build the tangent line at x equals 1. So that means that we need the function f of x. We need the derivative, which is going to be 1/2 x to the negative 1/2 power. We can write that as 1 over 2 root x, same thing. What we're really looking for is not so much those functions, but the values, f of 1, which is square root of 1, and f prime of 1, 1 over 2 square root of 1, which is 1/2. So the tangent line at x equals 1 is going to be y equals f of 1 plus f prime of 1 times x minus 1. F of a plus f prime of a times x minus a. And in this case, we have 1 plus 1/2 x minus 1. So this is our tangent line approximation to the function at x equals 1. So how do I use this? Well, we said that we're going to try to find that yellow dot there. And that yellow dot is going to be plugging in 1.1 into the tangent line, which is an easier thing to do. So let's do that, and we'll kind of talk about why that's true again in a second. So we do that, that's going to be 1 plus 1/2, 1.1 minus 1. Now, it may be some people's initial thought to distribute this 1/2 to the x and the negative 1. And although that's going to give you the same answer, leaving it in this form x minus 1 is actually nice because we're going to be looking at points that are close to 1, and this algebra is actually much easier to do. This is 1 plus 1/2 times 0.1. That's going to be 1 plus, this is the same as 0.5 times 0.1 is going to be 0.05. So this is 1.05. Think about it a slightly different way, or have a formula. We're saying that the square root of x is going to be approximated by the line 1 plus 1/2 x minus 1 near x equals 1. Near that point, the tangent line is approximating the function. So this means that the square root of 1.01, well, I think I did 1.1 in the example. Have an extra 0 there everywhere. If we do 1.01, this is going to be approximated by plugging in 1.01 into the line. Yeah, and it should be 1 plus or 1.005 here as the answer, as the approximation. So note, if we go back to the previous page real quick, we can see that this was indeed the tangent line that we came up with, right? We have the special point 1, 1, the function square root of x, and we are looking at, say, a 1.01, which is not quite there, but we can think about the actual value and kind of zoom in, the approximated value. And we can see that in this example, the approximated value is an overestimate. Because it is above the actual function value. This is an overestimate. So the nice thing about this problem is it really allows us to get to the tangent line, allows us to do some information, but in all actuality, sorry about that, I was saying that this example is not terribly realistic because we can just plug in square root of 1.01 into a calculator. So what might be an example that is more realistic? Let's look at this one right here. We're going to have f of t is going to be the rainfall accumulated since midnight. We know that at 10 a.m. there is 6 centimeters of rain on the ground, and the rate at which rain is falling at that time is 0.4 centimeters per hour. We're going to use that information to estimate how much rain will have fallen at 11 a.m., at 3 p.m., and at 10:15 a.m. So note that we do not know much about the function f of t. All right, and this is going to be a more realistic kind of thing where it's not like a function where we just have all the information for it. We don't really know much about f of t. But this is actually something that we've done in a previous section in chapter 2. So let's think about it. First of all, at 10 a.m., we're saying that t is equal to 10 hours, right? T is equal to 10. It's the hours since midnight. And we know that f of 10 is equal to 6. At 10 a.m., there's been 6 centimeters of rain on the ground. We also know that the derivative at 10 is equal to 0.4 centimeters per hour. And that's really all the information that we have about the function f of t. So how can I approximate f of 11, the number of, or how much rain has fallen at 11 a.m.? That is f of 11. Well, we could say that it's going to be whatever the value was at f of 10 plus how much it's changing per hour. So in this case, it is changing at 0.4 centimeters per hour. So we could approximate this with 6 plus 0.4. Or we could approximate this as 6.4 centimeters per hour. All right, so let's just do the rest of these. How could I deal with 3 p.m.? Well, note at 3 p.m., this is going to be the same as 15 hours past midnight. So f of 15 is going to be about our starting point, f of 10, plus 0.4 times how many more hours we have to go, which is 5. In the previous example, we only had to go 1 hour. In fact, I should write here f prime of 10, 5. We're only going 1 more hour. That's why we could just be able to use 0.4. Now we have to multiply that by 5 to get 0.4 every hour. This will give us 6 plus 0.4 times 5, which is going to be 8 centimeters. Sorry, that's not per hour, just centimeters. All right, so how could I deal with 10:15 a.m.? Well, what even value is that? That's going to be 10 point a quarter of an hour, so 10.25. And at that time, again, we could say that we're going to start with f of 10, and we're going to add the derivative for how many hours? For 0.25 hours. This will be 6 plus 0.4 times 0.25, which is going to be 6 plus 0.1, or 6.1 centimeters. So what's really going on here is that we are estimating f of t with f of 10 plus f prime of 10 times the difference between our value we're looking at and 10, or t minus 10. And this is exactly the tangent line of f of t at t equals 10. In this case, we had 6 plus 0.4 t minus 10. And this is a good approximation when our time is close to 10 a.m., and it's a bad approximation the further we get down the road. So f of 15, this may not be a good approximation. F of 10.25, this is probably a good approximation. And the closer we are to 10, the better approximation we'll have. All right, so one last thing we need to think about is error. How far away are we from the actual answer? So suppose that f of x is a differentiable function. We need differentiable because we need to be able to take the derivative of the function. For values near x equals a, the tangent line approximation, that is the local linearization to f of x is going to be approximated by the tangent line f of a plus f prime of a times x minus a. So the error is going to be the difference in those two values. The actual value minus the approximation. So if that error is positive, that means that actual is greater than approximation, which is saying that we have an underestimate. And that's going to happen if we have a function that may look like this. We have our function, we have our tangent line, and this is the tangent line lies below the function. And this happens when f is concave up. So we can determine if this tangent line approximation is going to be an under or over estimate by just thinking about the concavity. When the approximation is less than 0, we're saying that the actual value is less than the approximation. And that's going to happen when the function is concave down. The tangent line is going to lie above the function at that special point, or near that special point. So we're going to have an overestimate when f of x is concave down. And if we go back to the first example we did today with the square root of x, we saw square root of x is a concave down function, and the tangent line lie above that function. And we saw this is going to be an overestimate. In the next video, we'll look at some practice problems related to the tangent line approximation.